All right, welcome to Computational Complexity in the Query Planner. First, a little bit about me. My name is James Coleman, and I'm a software engineer at Braintree Payments. We process credit card transactions, and if you took Uber from the airport into town, we probably charged your card, but you didn't know. I'm on the database team at Braintree, hence why I'm here, obviously. Today, here's what we're going to look at. First, we're going to take a brief overview of computational complexity. Then I want to look at the operation types that the planner has available to it when executing your query. We're going to talk through a couple of sample queries and the plans that they generate. And then as a bonus, at the end, I'll talk through a few ways that you can make the planner do what you want when it otherwise doesn't. And as a note here, on the database team at Braintree, I tend to approach the database from the application side. So along the way, I'll make some observations about ORMs and how applications tend to access the database. And hopefully this will help you as you use it that way. I'm hoping at the end of this talk that you'll have a working knowledge of computational complexity, that you'll understand how computationally complex all the primary operations the query planner has are. I hope that you'll understand how to read explain plans if you don't already. And I'm hoping that you'll take away a focus on thinking about the structure of your queries before you even look at an explain plan. So first, computational complexity. The goal of computational complexity is to measure algorithm cost. It's a way that we classify algorithms by the number of computational steps that are required to process inputs as a function of the size of the input. Now, a few notes here. We usually think about the number of computational steps of an algorithm in terms of time, like the number of seconds that it takes to execute your query. But in computational complexity as a field, this measurement is usually actually just a number of operations, like the number of numeric comparisons that you make, or the number of times you access memory, or a combination of these kinds of things. Similarly, the size of the input might range from the number of bits, if you're, say, doing an add or a multiply, divide, that kind of thing, to string length, say you're counting the number of characters in a string, or in our case, we're going to define it effectively as the number of rows that you need to access or look at or process. We express measurements of computational complexity in what's called big O notation. Some of you who are more familiar with this may also hear big theta, some other terms that actually talk about like min and max. We're going to ignore all that today and just focus on the kind of more general case here. You would write it as O of n, where n is the input size that we just talked about, and the result of that function O is the number of computational steps, or in our case, effectively the rows that we're going to look at. A few rules for writing this. We only care about the most significant terms, and we drop all leading coefficients. So for example, if you have something that looks at n squared plus n rows, we don't really care about the plus n. We only care about the n squared. Similarly, with 3n, it just becomes n. And we do this because if you graph out those examples, and we'll look at a graph here in a second, the resulting term, like the n or the n squared, will be by far the most impactful to the angle of the graph as the input size grows. So you can find this chart on bigocheatsheet.com. And my one irritation with it is that it doesn't actually show labels on the x and y coordinates. And an astute observer will notice that the size, the rate of change on the x and y axes are not the same. But that's because if we actually used like just a standard 1-to-1 ratio on both sides, these lines here in the red on the left would be basically straight lines up the graph, and they wouldn't be very easily distinguishable. So we actually stretch it out a little bit to make it more obvious what's going on here. I have taken this same color coding and used it as in the rest of the presentation as we talk about the different complexities of the operations that we're talking about. And it basically goes from green is like the best to red is the worst. So what operations can the planner execute, and how do they relate to the stuff we just talked about? We'll look at two major categories of operations. First, table scans, since we want to be able to read our data, and then joins, and we'll talk about the different strategies Postgres has for both of those. So first, the different ways in which Postgres can scan your table. There are 3 different ways that Postgres can scan your table, and the first is the sequence scan. It's the most fundamental operation in Postgres and really in any database because you can implement any filter operation with a sequence scan. It might be slow, it might be painful, but it will work. And it's also a simple algorithm. We just loop through every tuple. Typically, I should have put this in parentheses, I guess, but in Postgres, this is going to be in on-disk order. So we just loop through all the pages on the disk and look at every single row in each page. Our complexity here is O of n. If there's 100 rows, we have to look at 100 rows. There's nothing special or magical. It's most efficient when a high percentage of the table matches the filter terms that we've defined, or when the total number of tuples in the table is small. And we directly scan the heap or the on-disk storage of rows. But it turns out that we generally prefer not to have to process 500 million rows for every query if you have a 500 million row table. And so we implement indexes. And we're only going to talk about B-tree indexes today, since they're the default in Postgres and the most common. With indexes, we maintain a separate structure on the disk that allows us to perform our filtering more efficiently. And with B-trees, we walk the ordered nodes on disk to find matching tuples. They're sorted on disk, the ordered part, and we seek ahead to the right spot and then only look at the part that matches our filter. If we need to look at one row, the complexity of this is only log n, and you can see it's green. This is like the best operation we have available to us if we want one row. It's most efficient when a small percentage of the table matches the filter terms. But you have to indirectly start with the index and then follow pointers to the heap. This is why small tables are often better accessed with an index scan, because even if I have my 100-row table and I have a B-tree index defined on some special key column, it turns out that because I/O cost is so high for, or latency is so high for I/O, I don't want to go read the index and then later go to the heap to look at what matched. I'd rather just look at the 100 rows in order. There's a variant of the index scan called a bitmap heap or index scan. And bitmap scans work by walking the index to find the heap tuples, or pages, and I'll talk about that in a second, with matching tuples, and then sequentially scans all of those tuples or pages. Tom Lane explained it this way on a mailing list. A plain index scan fetches one tuple pointer at a time from the index and immediately visits that tuple in the table. A bitmap scan fetches all the tuple pointers from the index in one pass, sorts them using an in-memory bitmap data structure, and then visits the table tuples in physical tuple location order. And the complexity here is a little hard to pin down because it depends on, one, whether or not the bitmap is lossy or not, and two, exactly how much of the table we have to scan and what we're looking for. So this can be as bad as a sequence scan, effectively, or as good as a regular index scan. I said I'd come back to lossy. So if we have the normal way that we would define this bitmap, so 0, 1, 0, 1, 0, 1 kind of thing, is that each tuple in a page is represented by a single bit. 1 matches, 0 doesn't. But if you have a big enough set of rows, even though you're only using 1 bit per row, at some point you run out of memory to store that bitmap. And so we can actually change to looking at pages instead and use our single bit to represent a page. This is really great for fitting into memory. It's really terrible if only like 1 row per page matches, because you now have to scan the entire page just because 1 row matched. It's most efficient when a reasonably large percentage of the index would need to be scanned, but only a middling percentage of the table will likely match. If we have to scan a large percentage of the index, this is beneficial because we get everything up front and then can read in on-disk order and benefit a lot more easily from disk I/O optimization by the OS. It also allows combining multiple indexes with a bitmap and or bitmap or operation. Since we just have our 0 and 1 bitmap, that represents rows, we can easily bitwise and or these together and come up with a reasonable approximation of things that are likely to match. It has to double check to verify at the end, but we can at least filter down that way. I've heard expressed before that it's fairly uncommon to be able to like valuably merge indexes this way, but in my experience, actually this can be quite valuable. Our queries would be pretty boring if we only ever scanned one table. And if we only scanned one table, it'd rather defeat the purpose of calling our database relational. So we want some joins. This is how we relate tables to other tables. And just like with table scans, Postgres has 3 primary ways that it can execute your join. But first, a few terms. Our outer relation, you also hear this described as the left relation, is the table that we're joining from. The inner relation or right relation is the table that we're joining to. And Postgres always drives the join from the outer or left side. That's not a theoretical limitation. It's an implementation detail in Postgres. And Postgres also only implements 2-way joins. If you need to join A to B and B to C, or A to B and A to C, then we just execute those as 2 steps. We join 2 tables at a time and then join the result of that with another table. There's no optimization that takes 3 at the same time and tries to push them together. Just like the sequence scan, there's a very basic join algorithm, the nested loop, that can be used to implement every join operation, assuming each side is driven by a sequence scan. And that would look like, for each row in the left relation, loop through each row in the right relation, and return rows when they match. The complexity of that would be n, so the size of our left-hand relation, multiplied by m, or the size of our right relation. But because we have multiplication here, like, again, the ultimate complexity of this depends on exactly what our tables look like. If the inner relation is like orders of magnitude smaller than the outer relation, then effectively we have an ON operation, and that's pretty nice. But in our worst case, if we have 2 similarly sized relations, this can become n squared and quickly become to the point where you don't want to wait for it to finish. It's most efficient when you're executing a cross join of a high percentage of both tables, since you have to return every possible combination anyways, which is an n squared operation. Or when the matching percentage of the outer relation is high and the inner relation is very small. It is possible to drive either side of this, though, with an index scan or a bitmap scan instead of a sequence scan. And in that case, we're going to take the complexities and add them together. Merge join is often called a sort or a zipper join. And it works by stepping through the left and the right relations in an ordered lockstep. Its complexity is the largest of the 2 tables effectively, which also, again, like many of these, assumes that if you have there's a certain case where it becomes O of n, in this case where they're similarly sized. This is a good example of where we drop the coefficient, because like if you're actually looking at n rows and n rows on both sides, then you might say this should be like 2n, but we just drop that 2 and call it O of n. It's most efficient when both the left and right relations are already guaranteed to be in some specific sorted order. And usually that's because each side is driven by an index scan on the join key in particular. And this is really beneficial when the ordering provided by the left relation is something that we want further up in our plan. So if we want to return a result set that is ordered by some key, and that key is also the same thing that is being used to join, then we can kind of get our sort for free and our join working off of the same thing. And that's really nice to do. But it's limited to equality join operations or conditions. Finally, we have the hash join. And with a hash join, we build a hash table of the right relations rows indexed by the join key. And then we loop through the left relations rows, and we probe the hash for each one to see if it matches. Our complexity here is O of n plus m again, which again resolves to n if we have similarly sized relations. You want this because it improves performance of a nested loop by memoizing lookups in the right side of the join. So if you don't have an index on the right-hand side of the join, this is a way to cheat because you only have to do your read of the disk once. But it's actually even useful when you do have an index on the right-hand side, because if we have a very large number of rows on the left and a very small number of rows on the right, for example, we don't want to have to do repeated index seeks for the same exact value. And with a hash join, we can eliminate that extra work of unnecessary index seeks. Hash joins are also only available when our join conditions are simple equality. So very few of these operations that we talked about have algorithmic complexity that look like good colors on the chart. There was a grand total of one operation that was green. And so it would seem like computational complexity is not our friend, but our enemy. But we can work towards becoming friends. And we do that by doing less work. We cheat. So we design indexes, and we talked about how indexes work. We want to, when we pick what indexes to build, we want to narrow the percentage of a relation as quickly as possible for the greatest number of queries possible. Ideally, we want something that will allow our queries to return either a constant number of rows or a constant percentage relative to new rows in our table. That is, we don't want the result set to remain the same percentage of the total table size as the table grows. If, for example, we're adding 1 million rows a day, we don't want to be adding 100, like 10% of that every time and retain the existing rows in the result set, because our result set just keeps growing and growing and growing and quickly becomes too large. But if it can grow at the percentage of growth only, then that's not necessarily terrible. Postgres can use multiple columns in a single index. And almost always, we want the lowest cardinality column first. We'll look at a reason why that's not, or why the inverse of that would be a problem later. Cardinality here, if you're not familiar with the term, basically just means the number of distinct values. So if we have a low cardinality value, we have very few unique values. Your primary key would be the lowest possible cardinality that you could have in your table. Postgres also has partial indexes. And I have an example here of how you would define that. Basically, we do our normal create index, but we add this where clause, and it only indexes rows that matches that predicate. And also, I can't see the parentheses over there, but they are there. Now, sometimes when we're building partial indexes, the thing that you would restrict on, that is the where clause here, this status equals pending shipment, often that would be like the thing that you would have intuitively indexed. You're like, oh, I want to filter on status, but I only care about things that are in pending shipment, and so I'll put status in my index. But if it's already the thing that we're filtering on with the where condition, it doesn't really make sense to put this single value in the index itself, since there would be no additional filtering, and we'd only have one key at the top of the index and just a big list of rows. And often I found that a simple solution there is to pick a column that you'll otherwise obviously need, because sometimes there's not something that you actually need, and in the query it's going to use this directly, like in the where clause. So I often choose the primary key if there's no other good candidates that I need in the query. So in this case, I've put ID in this index. And that way, not only do we get the filtering on the status equals pending shipment, but if we join to this table, it can use that ID value in the index to execute the join. We often use in and then a list or a subquery, and exists and a correlated subquery, or equals any and then an array to execute the same semantic value. But they can have different performance. Sometimes the planner magically makes them all the same, and it's actually pretty intelligent about, for example, turning a correlated subquery that uses an exist into something that isn't correlated, which always surprises me, like it turns it into a join. but sometimes it's worth playing around with the different ones of these. It's also really important, as a side note, that not in with a subquery and not equals any have different semantics. This is like very surprising to most people, I think, that if you have a null item right here in this not in list, versus like a not equals any, the not in will return no rows, and the not equals any will return the row that we cared about. And the reason for this is this null, because SQL uses ternary logic, and the definition of not null is extremely confusing in the SQL standard with how that comparison executes. So the TLDR here is don't use not in unless you can guarantee there are no nulls. Just use not equals any in an array. We often only care about a certain number of results. And so we have limit. The performance of limit depends on the nodes that feed the limit. And usually, the biggest driver of that is how you apply an order by clause. If no sorting is required or sorting is fully guaranteed by an index scan, for example, then limit can short circuit complete execution of gathering all those things and return early. And that's really nice. But if the full result set has to be built before applying the limit clause, then it won't improve performance other than the fact that you won't have to send as much data back over the wire to your client. Offsets are another feature in SQL that look compelling at first because they allow us to ignore the first end results in our result set. But it always requires the database to process all of the ignored tuples before returning any of the ones that we want. So I somewhat tongue-in-cheekily, but also seriously say that this is never efficient. And I just recommend that you not use it. This performance difficulty is actually inherent to the definition of offset. It's not something that bad programmers haven't fixed in Postgres. It's not something they can really improve by making the query planner more intelligent. It's built into the standard this way. Now, the obvious question here, if you're using offset, I would guess, is that you're using it for pagination. If, in fact, that's something that you're concerned about, feel free to ask in the Q&A. So I've seeded the Q&A this way. We often want to know, does a record exist? A single record exists. And ORMs often make it really easy to implement this as get the count of all the matching records and check to see if it's greater than 0 or not. But counting in Postgres is slow because the database has to process the entire matching result set, verify that all those rows are actually visible to you, and then return a count. So if we're looking to see if a single record exists, but a billion rows match, you just touched a billion rows. Instead, prefer exists and select one in a subquery with your where conditions, because it can actually short circuit when it finds a single matching result. But unfortunately, if no matches are found and that no matches was the result of scanning a billion rows, you don't actually improve your performance. There's no short circuiting that can help if you can't short circuit. So all this is well and grand, but how do we know what the planner is actually going to do? After all, SQL is a declarative language. We don't tell it what to do generally. And this is where explain comes in. Explain isn't part of the SQL standard. It's an addition that Postgres adds that returns a tree of the execution plan that Postgres is going to use to run our queries. We need to explain because of the declarative nature of SQL makes it inobvious how our query will actually execute. And the results of explain can often tell us whether or not a query will be likely to execute sanely, and if not, it can often point us in the direction of why it's not. But anyone looking at an explain plan for the first time will be tempted to go the other way again and forget that explain exists because this mess of output is messy. So let's walk through this for a second. First of all, our cost numbers right here, this cost equals and then a range. Cost is a bogus number, kind of like computational complexity measurements. It tries to munch together the time that it takes to do I/O to your disk, the amount of memory you're going to use, the number of computations the CPU is going to do, all into one number when none of those things are actually combinable. So don't read this as like 55 seconds or 55 milliseconds. It's just 55 some cost unit that nobody has a name for. The first number is the startup cost. This is the time, not time, the cost that Postgres thinks it will take to return a single row, the first row. And then the total cost is the time that it expects to spend returning the entire result set that will be returned. Our operations are over here on the left side. And we execute this from the inside out. So the first thing that's going to happen in this query is this sequence scan down here at the bottom inside. Then we'll build up this hash. Then using a seq scan, we'll walk through this order line items table and probe the hash repeatedly to execute this hash join and so on up the line. That is another way to say that the outer nodes pull tuples from the nodes beneath them. And that's just a way of saying that it depends on the node type, but not all nodes down here at the bottom need to execute entirely before they begin returning rows to the thing above it. The thing above it can ask it for a single row, and often it will not try to build the entire result set. There are a couple of other things that we can tack on to explain that are particularly useful. The first and most common is explain analyze. This doesn't just show us an estimated cost and row count, but it also executes our query, doesn't give us the result sets, but it does tell us the actual row counts that we encountered at each node, as well as the actual time spent in each node. And so we can actually see how things differed from what was expected. I also find adding buffers in particular here. Notice, by the way, that you can do explain analyze without parentheses, but if you want to add these other options, you have to parenthesize them annoyingly. I find buffers extremely useful, particularly when you're troubleshooting queries that are slow the first time and then get dramatically faster when you execute them repeatedly, because I can find out at what point it is accessing disk a lot more than was expected. So our first example. You can read this kind of complex query as, or in English as, find all of the orders for a batch of customers. That's that in list there, for which cash was paid. And the payment happened on August 27th, between the 27th and the 28th. And the current status is shipment pending. Now, I know it's not obvious in the query, but in this particular case, the author of this query was attempting to speed up the query using this restriction on created at, so that the database wouldn't have to look at quite as many rows. And here's the explain plan that we got for this query. Now, I've intentionally removed the cost and row count explanations that explain would normally give, because I don't actually think it's relevant in this example. Whether you've used explain a lot or not at all, I think it's a big trap to assume that cost and row counts allow you to ignore certain parts of the plan. So I encourage you to look at the plan and get a feel for its structure and what it's doing before looking at the cost and row counts. So a few observations about this plan. First of all, we have this sequential scan on order status changes. And the first time that we look at this, my first thought is, well, I have a seq scan on this table, and I'm using it to drive a nested loop. That feels probably slow to me. That's my first thought. However, the right side of the join is an index scan. And in this particular case, we're only going to find one row for each check. And so this nested loop is actually an entirely reasonable and even the right way to execute this most efficiently. The next thing I noticed is that we have a seq scan on a table that, I realize you're not necessarily familiar with the schema, but on a table that is probably quite large. If we keep track of every time the status changes on an order, then presumably this table has a number of rows that is like roughly equal to the number of orders times the number of average number of statuses that an order is in. So this will grow pretty fast, and I'd probably prefer not to have to seek scan over the entire thing. There are also a lot of random filters in here that we could theoretically turn into index scans instead, but it's not really obvious that many of them would be very general purpose or how you would define them in a general purpose way. The final thing I noticed is that we're trying to batch the query based on whether the order was paid, or when the order was paid, that created at that we talked about earlier. It's right here. But to get that restriction, the planner is doing a full sequence scan on that large table, and that's probably not ideal. In another test I did on this query with a slightly different data set, that restriction, that created at between restriction, was actually just tacked on down here at the end of the plan after doing everything else. And so that filtering was completely worthless. It didn't actually change the amount of rows that the database had to look at, even though that was the whole intention of adding it. In this case, it does restrict it a little bit, but it's still, but the way that that restriction is implemented is not great. So working backwards, I don't think we need explain to see the biggest problems in this particular query. First, the major filters are spread out across 3 different tables. We expect a small percentage of orders to be pending shipment at any given time. Presumably, this list of customer IDs is significantly smaller than our total number of customers. So we have a small restriction, a small restriction. We have another thing here on the same table. The payment type is cash. I don't know how many things are cash versus credit card, but like whatever. But then we have a third table here, and we do what is presumably a very limiting restriction also. Like we're limiting it to a single day, and presumably we have orders that change status on every day. So I think the biggest problem here in this query is that we have to join a large number of relatively poorly filtered rows, and that's always going to be computationally expensive. So if this is kind of your problem that you see, it's probably time to start thinking about how you modify your schema to be more efficiently queried, which is unfortunate, but reality. Here's another case with our orders table, but a little bit different structure this time. I've seeded this orders table with 100 million rows. We have several different possible statuses. We have paid, shipment pending, shipped, delivered, canceled. I don't expect you to remember all of those, but it is helpful to know that there are no, out of those 100 million rows, only the last 1 million, so 1 in 100, can even possibly have the status shipment pending, and it's actually not all of those 1 million. So there's a very small percentage of table, or very small percentage of this table that should match this status equals shipment pending check. So we can think of this query as something like find all of the orders that have been packaged but not yet shipped in the last 20 days. And the query plan we have down here is incredibly reasonable. We use a bitmap index scan on this index I've defined that has status, our low cardinality column, and a slightly higher cardinality column created at. And those 2 columns match exactly the 2 columns that we're using in our query filters. So everything matches up really well here, and it executes well. I don't have total timing here, but it's fast. So to make things a little bit more interesting, I've added a limit clause, and we only want to return the first 1,000. And the query plan actually this time gets better. Earlier, I mentioned that limit can sometimes short circuit executing the full node underneath it. And that is what's happening here. And here's how you know that it is happening. What we don't want to look at, we don't want to compare the number of rows at this limit node with the number of rows in the node below it, because the number of estimated rows for our limit is going to be the number of rows that we are returning, which is a reasonable assumption. So it probably will be smaller than this number. But if we look at the costing numbers, this 2,500 roughly number here as the total expected cost for the limit node is orders of magnitude smaller than the estimated total cost of the index scan below it, which is something like 726,000. And this is our clue. Postgres doesn't tell us explicitly, but this difference, this several of order magnitude difference between these two numbers is our clue that limit is actually not going to execute this entire index scan, find all matching rows, and then just give us the first 1,000. Now, as a side note for extra interest, if you change the status condition in this query to check for the status being shipped instead of pending shipment and run explain, the planner will generate a sequence scan. Because it's aware that lots of rows match that status, that much is true, but it's not aware that that status condition combined with the created at condition here, in the last 20 days, will actually mean that the majority of rows early in the table will never possibly match. And while I don't show it here as a demo, that becomes a very slow query. And that actually is an issue that one could theoretically fix in the planner with better statistics, but it's not the problem that we're interested in right now because it's not something we can change. Building on this query again, now not only do we have a limit clause of 1,000, but I've added this order by ID ascending clause. This kind of query is particularly common in ORMs that make it easy for you to either batch through a query result set or do pagination for you. But this is where the query plan falls off a cliff. When we first look at this, I see an index scan as the thing that's driving this. And if I stop there, I would think that everything is working just as well as before. But then I look at the index that it's chosen, and it's chosen the primary key index, which is not expected. And this query, while it says it's an index scan, is effectively executing a sequence scan behind your back. And in fact, it's actually worse than a sequence scan in some sense, because the I/O indirection of indexes that we talked about earlier means that it not only has to read the entire index, it also has to read the entire table. The planner is choosing to execute this way because it needs to provide a total ordering on the ID column before it can know what the first 1,000 rows are. And this failure is not particularly a failure of the planner, it's our failure. It's inherent to the query, and it's not something that we can fix in the planner. This kind of query construction asks the database to care about completely unrelated columns in the where and order by clauses, and the result is that there's no good way to execute the query in a general case. Like I said, it's common with ORMs. This is something I see frequently, and the cynical side of me would say to ditch your ORM at this point. When we page or batch through results like we were talking about in the previous one, we want to require a stable sort. And that's in fact what that order by ID was doing in the previous query. This query is something like find the 50 most recent values for a specific customer. And we have the order by created at descending, which is really all we care about if all we care about is presenting some like nice to view list. But if we care about pagination, or we care about the fact that refreshing the page may generate different results, or going to the next page may mean you miss a row or see a row twice, then we have to add another order by clause, this ID descending. And we add an index on orders with customer and created at, the customer ID and the created at. And we reasonably, I think, expect that this will execute in a very sane way. So let's see if we're correct, other than the fact that I've already told you the performance is terrible. So we look at this, start at the bottom with bitmap index scan, and it uses the index that we wanted. So far good. We keep going up the line, and we see that we have a sort. This is our first indication that something may not be great. But after all, we did ask it to order by, so maybe sorting is OK. So then we look at our limit node, and this 6,300 number is not really all that different than the total number at this sort node. And so we can conclude that the limit did not actually short circuit. We found all possible results and then applied a limit. So the limit didn't help us at all. Now, we can fix this in a non-general way by changing our index definition to have ID tacked on the end. This results in an index-only scan backwards. We didn't talk about index-only scans earlier, but effectively it just means it's not going to actually verify data on the actual rows in the heap. It doesn't even need to touch the heap for the query that we're executing. And it's going backwards because we asked for order by descending. And we apply the same check here. We look at the limit number total cost, and it is significantly smaller than the total cost of the index scan below it. And so we can conclude that we're doing well here. This limit is actually making our query faster. So our performance is good, but we don't want to have to define every single index in our system with our primary key tacked onto the end. That's a good way to make indexes slower to build. It's a good way to chew up your disks unnecessarily and just to cause yourself a lot of pain. So we want to be able to use more generic indexes like customer ID and created at, but we also want to have our cake and eat it too. We want stable sorting also. We don't want a result showing up on 2 pages or on no pages at all. So I propose the following solution. We can find the first n plus 1 results, where n is our limit n. If the result right after Rn has a created at value that is different from that same column at the nth row, then we can just return the first n values and sort them. If those 2 values are equal, we can gather some more results until we find a new date value. And once we found at least one more distinct date value, we can sort all of these results by both the created at column and a tiebreaker and return the first n values. And this is in fact possible to do with a recursive common table expression. I am not going to walk you through this gargantuan mess, but suffice it to say that it does work, and I have used it in production code, and it makes things a lot faster, but it's disgusting and hard to use. So that recursive common table expression solution works, and it works on stock Postgres, yay, but it's complex and nobody wants to use it. So our only alternative is to fix the planner. And there is a proposed patch that's been proposed in various iterations for several years called incremental sort, and you can find it in the current commit fest at this link. This patch, unlike the recursive CTE that I showed in the previous slide, doesn't require executing the base query multiple times. That is, if there's a tie breaking needed, the CTE will actually execute more than one query within itself. Instead, it just sorts in batches, and it short circuits when it knows that it's no longer possible to need more rows to guarantee the proper sort. So that's pretty fantastic, and you should go review it and tell people on the mailing list that this is an important patch. Another example, sometimes we want to find all of the distinct values from a fairly low cardinality field. So in this case, we have a query that asks how many customers that we have actually placed orders. And to test this out, I inserted 10 million rows into this table and equally distributed them among 10,000 unique customer ID values. Kind of boring, but it proves the point. And I created this index on customer ID, naively thinking that it would be useful. And then I executed the query and found that instead it used the sequence scan on our orders table and ran through the entire table. The row estimate is actually pretty on here. It's very close to our 10 million number. It looks at every single one of the 10 million rows to give us a result of 10,000, roughly speaking. So this is not great. There aren't many distinct values, and it seems entirely reasonable to me to want to be able to use that index to find those distinct values. So I propose this solution. For each key in our index, we can check tuples until we find a single matching visible row. As soon as a single visible row is found, we can walk back up the index tree, B tree, and go to the next index key and keep doing that until the end of the index. And here again, we can actually implement this in stock Postgres with a recursive common table expression. This one is not my design, unlike the last one. This one is actually, this query is actually on the Postgres wiki. and I've just applied it to this situation. And this also works, albeit this side of the query, it will execute one time for every customer ID. So if it turns out that your value does not actually have low cardinality, it turns out that you have almost as many customers as orders, then this won't be great. You really want the seek scan in that case. But assuming this is a normal system where like you have repeat customers, then this will work pretty well. But again, and the query plan that it does, this is a lot to churn through, but the short of it is that it does execute in a reasonable manner. That works, and it works on stock Postgres. But again, it's complex. This is a repeated theme. And our alternative here is also to fix the planner. When I started working on this talk, there had been talk for a long time that the proper solution to this is an index skip scan. But no one had ever worked on it. And then I went back to find the code again and noticed that there was now a link to a patch. So this patch is actually new as of middle of the summer, I believe. And just like the last one, it also doesn't require executing the base query one per time. And because it's built into the planner is aware of the cardinality of your values and can decide to use this approach or not, depending on whether or not it's appropriate. So, in conclusion, I have a few concluding thoughts. First of all, I think computational complexity matters. It's not just an academic subject, because you can't cheat the cost of algorithms. They are what they are. I also think that the planner is actually very intelligent most of the time. It surprises me that it can do a lot of the things that it can do. And because of that, when your query is slow, my first assumption is that my query needs to be rewritten, not that the planner needs to be fixed. So I look at my query, and I try to understand how it would execute, even though it's declarative. And then, after I have an understanding of what the query is doing, I use explain and see if my theory is confirmed or significantly off. But sometimes the planner really does need some help. And if you have an example like this or a query that does not seem to be executing reasonably given all these things, please email the Postgres performance mailing list and ask. People working on these patches don't know where the pain points are in the planner unless you tell them. So that's the end of the material I have for today. Any questions? If you have questions, actually there are microphones on either side here if you could use those so that the audio is on the recording.
This was really cool, actually. It's not a question and a comment. Last page is just super. I have stumbled on these issues, so I'm very glad it's actually going out, because that was very much missed. So like in these situations, not using indices is like dumb. And that's one of the rare situations when the planner is not doing the right thing. Actually, right. I 100% agree. That's advice I'm always giving, like check it out, because sometimes actually, I like to say people are creative. Sometimes they write a query in such a way that no optimizer can make any sense out of it. So like that's like totally like on the mark. So yeah, thank you for this. That's cool.
Thank you. Anyone else? Make yourself see, because the lights are in my eyes and I can't necessarily see you. Could you use the mic?
For pagination and the issue with the offset, what other alternatives to use just?
What other ways to execute it?
To achieve the same.
Yeah, so offsets would seem to be the natural way to execute pagination, right? Like they make a lot of sense, and they're like exactly what you want. The most common approach, and I think the best approach, is that you actually want to keep track of the last, the most recent last primary key value that you have, and just add a where primary key is greater than or less than or whatever that value. If you're sorting by something other than primary key, then you can get into some more complicated math and do like a lot of stuff to make sure that you're at the next value with greater than or equal to kind of clauses. Although even then, that's where you get into the stable sorting questions and really want incremental sort and stuff. But yeah, in general, you want to apply some kind of ordering and then use a where clause to filter out the previous things.
Thanks.
All right, I think we're out of time, so thank you for coming.